तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, in the previous lecture we have been working out an example of a direct mapped cache also, right. Fine. Specifically the example was talking about in case the block size is 32 bits, right, that is what we took for a block size of 32 bits. Okay. Now, what is this block? Essentially one unit of information that passes between two levels. Now, here we are talking about between CPU and the DRAM or the main memory, okay, that these are the two levels. Fine. Yes, we took this block of size 32 bits. But then we also said earlier that generally the memory is organized byte oriented, that is byte organized memory. That is, any time we may be interested in getting at a byte of data. Now, when we have 2 bytes, generally it is called a word, and then when we have 32 bytes, okay, that is 2 bytes is 16 bits, right. When we have 32 bits, then it is called a long word, and then 64 bits very long word, and so on and so forth. Okay, these usage keeps varying. Though we may have word, long word, very long word, but generally we are also interested in accessing at the byte level. So, what exactly is the data that will be subsequently used by the processor depends on the processor size. Okay, good. Now, we do not know just from by saying that the cache has 32 bits what exactly the CPU deals with. It may be 16 bit, it may be 32 bit, it may even be 8 bit or 64 bit, whatever it is. Okay, nothing is known about it. Now, when a program is organized and then subsequently executed instruction after instruction, then we have also seen that the subsequent instruction cycles will involve instructions in adjacent locations. So, as far as the CPU accessing the data is concerned, fine, it is meaningful to assume that subsequent bytes of data in the memory will be accessed. So, this is what we are explaining earlier as the principle of locality, that is something which is local. Okay. In this particular case, that is something which is immediate or next word, next byte, and so on so forth, okay, based on the principle of locality. So, when we say that we are assuming we are organizing the block size as 32 bits, we know that it has 4 bytes. Okay. Let us assume that the processor is also a 32 bit CPU, then it is meaningful that the processor always accesses the 32 bit data, and it is also meaningful to assume that subsequent 32 bit data will be accessed. The probability of accessing these neighbor things is very high. So, why have a data of only 32 bit, why not have the subsequent 32 bit information also stored along. So, we move on to the next one, in which we say if the cache, okay, is organized such that it has 4 words. Now, here what I am saying is word is 32 bit, okay, for 4 words per block. Now, in general it is more than one, that is what you have to see, that is multi word, right. Now, if you assume that the CPU, a 32 bit CPU was dealing with this cache, then it is possibly all the time it was accessing one word of 32 bit size, that is what it means. From the CPU point of view, the word, from cache point of view it is the block, okay, one 32 bit word. Now, assuming the same CPU, now this has 4 words in a block, CPU will access only one word at a time, okay, that is a different thing. But what comes from the DRAM at any time into the cache will be 4 words, that is what it is. So, now as I said, we can take it as multi words, okay. If you think that is a 32 bit word as a single word, now here we are talking about multi word, right. Why have multi word? As I said, it is meaningful to assume that the next or immediate data will always be accessed, right. Good. In which case, let us work out the problem again. What is it we had assumed earlier? We assumed for 32 bit data, okay, for 32 bit data, just I am rephrasing the problem which we had worked out earlier, and we also assumed a 32 bit address, okay, we had assumed a 32 bit address, and the problem was about, in case we have a cache of 64 KB data size, okay, cache of 64 kilobytes, this is only the data part of it, the data field of it, okay, that is the one. Then that is just the data size is 64 KB. Then the question was, what is the size of cache, meaning this is what we worked out. Now, this means essentially assuming valid bit is 1, what will be the size of the tag bit, that is what essentially it will boil down to. This, for this only we had worked out the problem. Now, we had worked out the previous problem assuming we have only 32 bit in each data field. Now, since we are taking 4 words, we are talking now about 4 32 bits, okay, of data available in one block, okay. Now, let us work out the detail as before. Now, the address is given as 32 bit, right, okay. So, let us see which, oops, that is bit 1 to bit 32. Now, this is the address part. Now, let us see what possibly the cache consists of. We know that each cache location must accommodate the valid bit, okay, just one bit, right, valid bit. So, let us call it V bit. Then we have the tag field, and then we have the data. For this problem we assumed 4 words per block. So, each block consists of valid field, tag field and data field. Now, this data field, okay, for this problem will have 4 words, okay, good. So, 1, 2, 3, 4, each of 32 bits, okay. This is the 32 bit data, this is another 32 bit data, this is another 32 bit data, this is another 32 bit data. So, we have 4 of these, okay. Now, earlier we had only 32 bit in one field. So, actually 32 bit means essentially that consists of 4 bytes, right. So, as before, whatever we had worked out earlier holds good now. For identifying which of these 4 bytes, we have to allow 2 bits in the address, and that we called it as byte offset, okay. byte offset. Good. Now, the cache will consist of many blocks like this. Now, what is the size? It has been given to us that cache of 64 KB data part, that is the data part alone is 64 KB, right, which we worked out earlier. Now, so we have, from that we can see how many blocks are there, that is we have 64 KB, that is this part alone, okay, data part alone, and each block consists now of 4 bytes each, right. So, 4 of 4 bytes, that is 16 bytes, okay, each block has 4 of 4 bytes. So, we have this divided by that will be 4 k blocks, correct, that is 4 and 4 16 bytes. So, we have 4 k blocks. So, there are actually 4 k blocks here, and to identify which of this block we would need, that is 4 k means we would need how many bits, 12 bits, right, because 4 k is 2 to the power 12, and so this means we need 12 bits to identify which of these blocks. Okay. Now, once you have identified which of these block, within the block you have to identify which of the 32 bit data, is it not? So, within that block, so there are 4 such. So, we need 2 more bits, specifically bit 3 and bit 4. Now, this is our block offset, okay, that is our block offset. So, the first 2 bits identify in the address, first 2 bits identify which of the bytes within 32 bit data. The next 2 bits identify which of the blocks, within a block which of the 32 bit data, okay, that is the block offset, and then we would need 12 bits to identify which of the blocks, okay, because with that 4 k blocks can be identified. So, starting from bit 5, if you say 12, that means it will go up to 16, right, bit 5 to bit 16. So, you will be having 12 bits here. So, with these 12 bits you identify which of these blocks, okay, which block, and for the direct map cache arrangement we would be using the remaining part 17 to 32, which means another 16 bits, right, these 16 bits in the tag field, this 16 bits is our tag field, okay. Now, when an address comes, yeah, we already talked enough about valid bit, we knew why, okay, we have seen that, fine. Now, when the CPU places the address, right, then the corresponding tag field of it will be seen, right. It goes like this. Now, you remember the direct map cache, at any time from 1 of n, okay, memory DRAM locations, the cache contents will be which one, this is what we have to know, okay. That information we had seen earlier enough through many examples how to identify, okay. Now, it is possible that in a given block, okay, any block you take, any one of these 4 k blocks, any of these blocks, the required content may not be there. Okay, what exactly is required is indicated by the tag, right. In our examples we have seen earlier, for instance, in location cache location 4, the contents of 4 may be there, or 14 may be there, or 24 may be there, or 34 may be there. So, in that tag we have seen in our previous example, right. It will be 0 or 1 or 2 or 3, that is the tag information. So, this 12 bits of the address placed by the CPU will indicate which block, that particular block, whether it has the required information or not, will be indicated by this tag. So, what is called a hit now? If the valid bit is 1, okay, if the valid bit is 1 and if the tag field of the given address and the contents, okay, of the given block, if they match, okay, if these two match, because this what we have here is the cache content, this part is the data, this part is the tag and valid. Okay. We will work out shortly the size. Okay. So, for a given block, if the tag of the incoming address and the tag content in that particular block, if they match and if the valid bit is 1, then this situation corresponds to CPU having found what it wanted in the cache. So, we say then CPU has achieved a hit, right. Otherwise, there is going to be a miss. When will it be a miss? The valid bit may not be 1 if it is 0. Now, this is one situation when, to start with, the RAM contents may be anything random, and if valid bit is 1, the tag fields may not match, the tag field of this the contents of the tag field of the block and the contents of the tag field of the address, they may not match, in which case the block contains some other locations data, that is what it means. Okay. So, in which case there will be a miss. So, this in fact summarizes the hit situation. If valid bit is 1 and the tag match, the two tags match, then it is a hit. Okay. Incidentally, now that we have seen that tag field is going to be 16 and then this will be valid bit is just 1. So, 1 plus 16 plus 4 into 32. So, so many bit wide is the cache, and then you have 4k of this, right. 4k blocks are there, no, the cache contains 4k blocks. So, 4k multiplied by, add up all these. So, that will be the cache capacity. So, now you can see that though essentially the data is only in this portion, you need all these extra things, mainly because we want to see that the CPU can run what it wants to run at the highest speed that is possible. Okay. So, let us work out another example in which we will see the how exactly to calculate the block number given a byte address. Okay. So, suppose we consider a cache. Okay. Let us consider a cache with 64 blocks. Okay. 64 blocks are there in that cache, and what is the block size? So, suppose the block size is say 16 bytes. Okay. So, the block has 16 bytes. 16 bytes, yeah, it is not different from what we have got here. Is it not? Each is 4 byte and there are 4 words. We are talking about similar thing, same thing. Now, given this, what is the block number for a byte address? We have to know that. So, you are being asked to find out the block number, okay, block number for a given byte address. What is the byte address? For the byte address, what is the address? Let us say 1600. So, that is the question. That is, given a byte address, we have to know in which block will it come. Okay. The previous example, we had as many as 4K blocks, okay, 4000 and all. But here we have only 64 blocks, okay, that is the difference. Okay. Now, how do you go about? So, the way to do it is take the byte address, okay, what is that 1600 in our case, and divide that by the block size, right. Then you will know which block it is. That is what we are talking about is take the byte address, that is 1600, divide that by the block size, which is in this particular case 64, okay, 64. Okay, 1600 by block size. Oh, no, 64 is not block size. The cache size is 64. The cache consists of 64 blocks. The block size is only 16 bytes. Okay, good. Once in a way, it's good to do some mistake. Good. So, block size is 16. Now, 1600 by 16, of course, is easy number. You get it as 100. Right? Where is say 100? The cache consists of only 64 blocks. So, how do you do it? Basically, it means in a cache, the 64 blocks are filled, and then for 100 actually roll over and fill in, right. That is what it means. In other words, mathematically we have come across this situation earlier. So, if you want to calculate the actual block number, okay, because essentially what we have is only 64 block. So, the actual block number must be calculated as 100, what is it, we have seen earlier, no, mod 64. This is the modular arithmetic, 100 mod 64, which means basically 100 divided by 64, and then you have a quotient and a remainder. So, the quotient will be, that is essentially the way to compute is 100 by 64. Okay. What you get is 1 and the remainder is 36, right, correct. Quotient is 1, remainder is 36. So, in other words, the actual block number will be 36. So, it is the 36th block, that is the one which will hold this particular byte address. Okay. Fine. As far as this cache dealing is concerned, what is it we have studied? We have only been reading from the cache so far. Now, what about writing into cache? Because the CPU would not only read, but also write into the cache. Now, for this you must know that we have the CPU. Okay. Now, the CPU accesses the cache, and we had said earlier, if cache does not contain what the CPU wants, so that will be accessed from the DRAM memory, right. Now, you see the problem. CPU wants to read something from the cache. If the cache is not does not contain, it will be got from the DRAM. Okay. Now, once CPU has got it in the cache, it can read, that is not a problem. Then the contents that the CPU reads from the cache and the contents in DRAM will be the same. Suppose CPU writes into that location in cache, then the cache contents and the DRAM contents will be different. Agreed? When CPU writes something into the cache, after all from CPU point of view it is just a memory, it can read or write. Now, in this particular case, if CPU writes into the cache, what happens? Then there will be a different number, okay, in the cache, different data in the cache, different from what was in the original memory. Situation is not bad. What happens at some point in time, the cache content will be removed, right, and then in that particular block another data may come. At that instant, the modified cache contents can be written into the DRAM. Okay, this is one way. Another way is, whenever CPU writes into the cache, it should also write into DRAM. Now, what is the problem we are facing in this? We know that CPU can write into cache very fast because this is fast memory, but writing at the same time into the DRAM, we know that it is a slow memory. The very reason why cache has come into being is to take care of the speed matching between the CPU and the memory. So, whereas CPU can write into the cache very fast, it cannot write so fast, maybe CPU or some other controller, it does not matter. So, the same content cannot be written into the DRAM very fast, and so we are again going into the problem of speed, that is mismatching speeds. So, one thing is, as it writes into the cache, it writes into the DRAM, do not mind about the speed, then it is called a write through cache. Okay. A write through, that is, as it writes into this one, okay, as it writes through into the, as CPU writes into the cache, the DRAM contents also will be modified or updated. So, in which case we talk about having a write through cache. Okay. So, you have seen whenever DRAM contents are also written when cache is written. The other one which I was suggesting is, whenever the cache contents are modified, correct, cache contents are modified, or the right word is whenever the cache contents are swapped out and the new contents come into the DRAM, at that time, okay, the data that will be swapped out of cache will be recorded in the DRAM. So, thereby you update the DRAM contents. Okay. So, the second one is called a copy back, that is, whenever we can specifically write copy back on swap out, that is, whenever the data from the cache contents are swapped out, you make copy back. Okay, good. Now, there is a small problem in this. What is that? Suppose there is an IO part of the program, okay, and if we find a specific block has been transferred to cache and it is active, meaning it is a valid block, it is being used by the CPU. At that instant, if an IO is required, okay, the IO would be, that is, the input output will be with reference to the memory, because this is going to be huge size memory. So, the cache is essentially for CPU's dealing. For IO part, things will be taken from the DRAM. So, at that instant what will happen, since cache contents and DRAM contents may not be the same, right, the updated data will be in cache, but DRAM may have outdated data which is not been updated. So, if you are waiting for copy to copy from cache into DRAM and update it only on swap out, then before swap out there is a possibility that some IO program may need reading from the memory which is not the updated data. So, there is a possibility of that particular thing. So, so there will be a problem in the second case in the copy back. What was the problem in the first one? Write through cache, we had already seen memory speed mismatching. The problem with copy back is there is a possibility that in case of IO the correct or updated data may not be output, fine. So, that is a problem with this particular one. So, what is done is, in addition to the various things that you have in the CPU block, right, like valid bit, tag bit, data, of course, that is the main thing. In addition to this, also introduce one bit called a dirty bit. What is this dirty bit? Introduce a dirty bit like valid bit, this is one bit, which indicates whether the cache contents has been changed or not. Actually, it means whether cache contents had been dirtied or not, that is what it means. In case there is an IO process which is going on, the first thing will be to check if whether that particular block is active in cache. If it is active, whether the dirty bit has been set. If the dirty bit has been set, it means the CPU has altered the cache contents and it indicates that cache contents and DRAM contents are not the same. So, if the dirty bit is 0, then cache contents had not been altered, possibly CPU has used it only for reading and it has not dirtied it. So, use that dirty bit, add the dirty bit in that block thing, fine. Now, you can see while talking about this, the advantage of having a single word and a multi word block. We were talking about earlier that it is very likely that adjacent words will be used immediately by the CPU and so it is convenient to have, but now it is possible that only one of these words has been altered and it will be indicated as dirty using the dirty bit, right. Now, while copying back, all the 4 words will have to be written into the memory, because at any instant a block basically means the minimum unit that transfers between 2 levels. The 2 levels that we are talking about here are cache and DRAM. So, suppose 4 words are going into the cache as a block, even if one word is altered, all the 4 words will have to be updated in the DRAM. So, like this you have advantages and disadvantages of different organization. Now, let us look at some more details of this cache organization with reference to these. Let us study this cache size and organization. So, this is the arrangement essentially we have CPU dealing with cache and then there is some communication between cache and the DRAM part. What was our essential objective? We have to see that CPU finds as far as possible all it wants in the cache. In other words, we want to make sure, this is our aim, right, we want to make sure that the miss penalty is as low as possible, that is the time taken in case miss penalty, it is time really, but we will not specific about that, specify that, miss penalty as low as possible, that is our aim, as low as possible. Now, we will actually calculate the penalty time, but that depends on some of the way we organize the cache under DRAM. So, that is what we are going to study now. Essentially, this being related to the time, we have got to have some data, basic data on which we can calculate the times involved. Okay. So, let us assume that the memory access times are as given here. Okay. Memory access time, because what is it that we are talking about? We want to see the miss penalty as low as possible, which means the time taken for getting the data is as low as possible. In case it is not, the CPU does not find it in the cache. Okay. Now, always for one address, some time is needed. Instead of really worrying about time in terms of seconds, we will see it in terms of the clock. Suppose one clock time is needed to send the address. Okay. So, we will make use of this data for all our calculation. One clock to send the address. Okay. Now, after the DRAM receives the address, let us assume that it needs as many as 10 clocks for accessing from the contents and putting it. Okay. That is, it is called memory access time, that is 10 clocks. What will be the clock? Okay. If it is 1 megahertz clock, the timing is going to be 1 microsecond. Okay. So, what will be that? So, let us say 10 clocks for each DRAM access, that is to get from the memory, that is taking 10 clocks, and let us say 1 clock is needed to send that word to the cache. Okay, 10 just for accessing, and then one more clock is needed to send the data, that is to send memory word to cache. Okay, to send the memory word, okay, that is from the DRAM. Okay, this must go to cache. No, only when it reaches the cache, the CPU can access that, right. So, assuming these timings, okay, we will work out. What else we need to know? We should say, you remember what we were talking about? We were talking about an one word block, 4 word blocks, multi word blocks in general. Now, the same thing about how many bytes can be accessed at a given time from the DRAM. Sometimes we may access only one word from DRAM, sometimes more than one word. Okay. Whatever that is accessed from memory, we will assume this particular bus width is such that, because the width of this bus. So, all these things we should know, we will assume that. Now, whatever we access from the memory, let us assume the bus width is such that whatever is accessed is passed on to the cache. Okay. Some assumptions. So, let us see, C is the width of the cache as far as the data is concerned, right. We are not bothered about the tag and valid, all those things are needed for organization. Suppose the cache width is C for the as far as data is concerned, and the DRAM width is D. Now, why are we talking about it? Because the RAM may contain 64 bits, the cache may contain 128 bits or more. So, these are independent. Okay. By having different values of C, different value of D, we are talking about different organization. Okay. We are talking about different organization, but we must be careful about this bus width. So, we will assume that whatever this access can be passed on, right. Fine. Let us work out the detail. Supposing that we are going to assume some different values of C and D, and then based on the access times we will work out the miss penalty. Okay, that is our job right away. Okay, miss penalty. Suppose C is 4 words, I am just saying words in general, okay, and D is 1 word. So, what I am assuming is, okay, let us say one word is a 16-bit word, in which case what we have here is a 64-bit, okay, cache. So, multi-word block, that is what it is. Suppose D is 1 word and C is 4 words. It is meaningful to assume in that case bus width is 1 word, because 1 word is going to be accessed at a time and that is being passed on. So, in 4 steps it will be put in the cache, that is what it means. Okay. Now, what is the miss penalty? That is, what we mean is the CPU is trying to access a word that is not available in the cache. So, from the memory address that is passed on by the CPU to the cache, that particular address will have to be sent to the DRAM, because it is not available in the cache, that is sent to the DRAM. So, one clock will be to send the address, and from that particular address the data will have to be got, and what is to be got, what actually goes between cache and DRAM? One block of information, and that block in our in this particular case corresponds to 4 words. So, only even if only 1 word is required by the CPU, the whole block will have to be replaced, right. 4 words will have to be read, because the whole block will have to be replaced. So, 10 clocks for each DRAM access, and then after it gets it, it takes 1 clock to send that word here, that is required for this transfer. In which case, what is the miss penalty is 1 clock is needed to send the address, and because the cache is 4 words, 4 words will have to be read from the DRAM, each of which will need 10 clocks, okay, 10 clocks. So, 4 into 10, 40 clocks are needed, and what else? So, those 4 words will have to be sent to the cache, which takes for each word it needs 1 clock. So, again here 4 into 1. So, I repeat, 1 clock to send the address, and because a block will have to be replaced, 4 words will have to be accessed from the memory. So, 4 into 10, 40 clocks, and again 1 clock each to send word to cache, and so you need 4 into 1. Okay. So, which means we have got, that is, this particular thing needs about 45 clocks. Agreed? That is the miss penalty. Now, if C were 4 and D also were 4, meaning we have a 4 word block and DRAM also 4 words can be accessed at a time, that is what it means, D is also 4. So, in that case bus width we have to assume as 4, right. So, in each case bus width will be different. So, we are not talking about it, right. If this is 4, what happens? 1 to send the address, 1 clock to send the address, and now 4 words can be read. So, it is enough if we read it only once, correct. It says each DRAM access. Now, in this case one DRAM access is going to access 4 words. So, only 10, only once a reading is to be done, 4 words will be got, and just in one step the 4 word will go into the block. So, now we have only 12 clocks, right, 12 clocks, good. suppose we have 4 words and DRAM is 2, right, C is 4, D is 2, then what happens? 1 to send the address and then 2 words from DRAM and forward block in the cache. So, twice from 2 locations it has to be read. So, we need 2 into 10 clocks, because for each access 10 clocks are needed. So, 2 into 10 clocks, and this will be sent in 2 steps, and so again 2 clocks are needed to send the word. So, that would be 23 clocks. Okay. Now, let us just go in for a slightly different organization here, the DRAM. Okay. The cache and DRAM part alone I will slightly alter. That is, suppose we have a cache and the DRAM consists of 4 different memory banks. Okay. 4, that is not a single one as we had assumed earlier. So, 4 different memory banks are there. So, they will be accessed. Okay. So, DRAM consisting of 4 memory banks. So, this particular one is in fact called an interleaved memory. So, now let us assume for that is we have 4 word cache, that is cache block is of size 4, and then we have here 4, but each one 1, that is what we mean. Okay. Each one is 1 word, but together we have 4. Okay. Each one only 1, but together we have 4. Now, as I said, this is called interleaved memory. So, let me, this is different from this case, just these 2 cases are different. So, here we have the interleaved memory, right. Remember, we had talked about this odd memory and even memory. Now, here we have 2 more things. Okay. Say location 0, location 1, location 2, location 3, like that, and then again 4, 5, 6, 7, that is what we mean. Now, what is the idea? Now, physically this has been separated. Suppose we had only 2, we can talk about odd bank and even bank. We have 4 here. Now, when you physically separate them, then once you put in an request for access, and simultaneously all the 4 can be read in parallel. Okay. Basically, it is a form of parallelism. So, once you address and forwards will be read in parallel, but what is being transferred, that will be only 1 at a time, that is the situation here. So, in this particular one you have 1 to send the address, and that address will go to all the 4 banks. So, all of them will get addressed, and then in parallel they are going to access the memory, right, in parallel. So, in unit time, that is taking 10 clocks, all the 4 will be accessed, but the access data will be passed on only 1 at a time. So, 4 clocks will be needed to pass on the word that has been accessed to be passed on to the cache. So, with this what is happening? We have only 15 clocks. Now, 4 different organizations we have here, right. That is 4 words, 1 word, 4 words, 4 word itself 2 categories, right. So, this is the way we organize, and now you can see how we can, by changing the organization, right, of cache and DRAM, we can go on ensuring that the miss penalty is reduced. Okay. That is depends on the cache size, the DRAM size, and also the memory organization. Okay. So, this is the main aim is to reduce the mesh penalty, for which you go to any length, any type of organization that you want. Fine. Now, once you have this, then we talk about the bandwidth, okay, the bandwidth, which is nothing but once you have the clocks, then how many bytes that can be transferred, okay, per clock. So, if you can express that, how many bytes are transferred per clock, then we talk about the bandwidth. It looks like, based on the various studies, the optimal block size, okay, the optimal block size of a cache is about 64 bytes. It looks for various things that have been studied. So, it is only optimal, it can vary. So, optimal block size of the cache, okay, in a cache is 64 bytes. Okay. So, this has come about in practical studies.